Some people still trickling in here, but let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1000. Hopefully you guys have had a good week. Let's actually jump in. Lots to talk about. Share my screen here. Okay. All right. So hopefully you guys are seeing that okay. Let me make sure that I can see the chat and the room. So whether or not everyone's here. Okay. All right. Awesome. So it seems like things are a go. Okay. So let's actually jump into it. So we'll first start with some, make sure writing is working. Okay. I was having some technical difficulties earlier, so I restarted everything, did updates, and I'm very just wary now of some other technical issue cropping up, but cautiously optimistic. I think everything is fine. But we're going to start with some public service announcements. So you should be aware that next week, Monday, college is closed for Columbus Day. So we won't have class. You won't have any class, in fact, so not just this class. So on Monday, you have a break. That being said, the following Wednesday will follow a Monday schedule. So whatever you would have done on Monday in terms of classes, including this class, that will be moved to Wednesday, October 14th. Our next class, quote unquote, you actually just have a quiz to do, the third quiz for the semester. And so quiz 3 is actually on Wednesday of next week. So that's very important. We don't normally have class on Wednesday, but you should just be aware on Wednesday next week at the beginning of the class start time, you should be logging into Gradescope to do your quiz. Okay. In terms of the quiz, it covers up to lecture 11, which you should watch by the end of today. However, lecture 11 towards the end introduces a topic, namely solving equations with rational expressions. That topic is introduced towards the end of lecture 11, and the examples spill over into lecture 12. So it's probably a good idea for you to watch the beginning of lecture 12. Also, however, technically speaking, you are only required to watch up to lecture 11 by the end of today. So that exam is going to essentially cover topics in 1.4 and 1.5, and I'll talk a little bit more about that in coming up. So our next Zoom meeting, the next time we meet here like this, is going to be on Thursday, a week from today, and it's going to be the day right after your quiz. Okay, so those are just some items in terms of scheduling. Let's move down. So let's actually talk about the quiz. Like I said, it covers lectures 11 up to lecture 11. It's technically 8 through 11. Of course, you will need to know things that happen before lecture 8 in order to be able to do some of these things anyway. But strictly speaking, I'm sort of testing you on 8 through 11. What that actually covers is 10 main things that I could pick out from those sections. So operations with rational expressions, right? So if I give you 2 rational expressions, do you know how to add them, subtract them, multiply them, divide them? Do you know how to simplify rational expressions is the second thing, right? Including compound rational expressions. So if I give you a rational expression and ask you to simplify it, would you know what to do? If I give you a rational expression that contains in it rational expressions, like fractions inside of a fraction, and ask you to simplify that, would you know how to do it, right? So things of that sort. Domains of rational expressions, that's kind of something that we've covered before, so nothing really to talk about there. Rationalizing rational expressions. So if I have a rational expression and there are radicals in the denominator or radicals in the numerator and I want to remove them, would you know how to remove them? Right, so that's also going to be important. Equations in general, but more specifically linear and nonlinear polynomial equations is what we dealt with, including quadratic equations, but this is just a special type, special case. You should know how to solve those equations in general. We'll probably talk a little bit about that. We also spoke about the quadratic formula. We derived the quadratic formula using completing the square. You don't need to know the derivation. However, completing the square is sort of something that you will need to know. If not for this quiz, definitely for like the next one that will cover circles and things of that sort, you should know how to complete the square for that. Equations with the radicals. So if I have an equation, there are radicals all over the place. How do I solve such an equation? equation with absolute values. I have an equation where there are absolute values all over the place. How do I solve those? And equations with rational expressions, which, as I said, that was started at the end of lecture 11, and examples spill into lecture 12. So those are kind of the main topics. If you want to kind of know, what do I definitely need to know for the next quiz? This list would be it. There's also a question here. Yes, so I would recommend that you finish up to 1.5 in WebAssign. Yes, and we will finish in time. And like I mentioned before, I'm deliberately going very slow in chapter 1 because really it's the foundations of everything that we'll be covering later. And if you fully understand the chapter 1 stuff, the other stuff will actually run through very quickly. So I believe your first exam actually mostly covers chapter 1, but there's a lot of details in chapter 1 that I didn't want to overlook. Yeah. Yeah, the quiz is going to be roughly the same length. I won't say it's the same number of questions, but I'm going to write it so that it's roughly the same length. And in any case, I could make it even a little bit longer because like we wouldn't have a Zoom class right after you take the quiz anyway. So I do have the option of making it longer. Technically, I can make it up to what you would have for class time, which is 1 hour and 15, but I wouldn't do that for a quiz. For your test would probably be that. But even if I do decide to make it a little bit longer to give you more time to work out some of the problems, it's a non-issue because you have more than enough time. Like out of the 1 hour and 15 minutes, I normally use like only 30 of it for a quiz. So that wouldn't be an issue either way. The topics immediately following. So topics after lecture 11, these would include things like inequalities, the coordinate plane, Pythagoras' theorem, distance and midpoints between two coordinates, circles and lines. So if you have covered all these 10 topics and you feel really solid and you're confident and you want to take a crack at the bonus problems, chances are I'm going to ask you questions about some or all of those topics that I just listed here. So that's just really extra. It's icing on the cake if you want a shot at getting more than 100% on a quiz. That being said, let's go into the Q&A. So I do want to talk about, just again, I go through, in class, I go very slowly through all of these guys. And so I'm not going to do anything in any level of detail today. I do want to talk about each of these very quickly and succinctly, like what are the main ideas that you should really remember. But before we actually get into that, any general questions that you have for me besides what was posted in the chat?
I have a follow-up question to
Yes.
Angelina. On C-Engage, so the test we have on October 19th, I think it says it's on the syllabus, it's up through lecture 12.
Yes.
Which from the video titles, I think is 1.9 or 1.10.
Right. So as of the lecture that you watch next Wednesday, that covers test 1. Yeah. So next Wednesday is the 14th. Right, so by the 14th, you would finish all the topics needed for the test on the 19th.
Also on October 19th, we have the C-Engage homework due. That is up through lecture section 3.2, which I don't think is until lecture 18. Okay, I'll have to review that. But if there's something like that, yeah, I wouldn't let any of the homeworks be due beyond what you would need for the test at that point. So, okay, so if there's anything like that, you can just like email me and remind me, oh, but by the way, it says that this homework is due and it's not even on the test. I can redate that. Thank you. Yeah. Okay. All right. But yes, good that you're reading the syllabus and you're kind of mapping out your schedule. But yeah, like the homework is due on the 19th. I'd rather you finish it before that and just spend that time up to the 19th just studying, going over some problems and stuff like that. But yeah, so the I wouldn't intentionally make due dates for any topics not on the first exam
due before the first exam. So if you notice any of those, you can just let me know and I'll redate them. I'll push the deadlines back. Okay, that being said, let's actually just talk very briefly, like I said, very quickly about the topics that I mentioned earlier that you'll need to know for the quiz, just so that we are all kind of on the same page. We all know the basic ideas that would be involved in these things. And this one was covered when we spoke about this before with fractions, but let's actually just start with operations with rational expressions. So these are basic things like if I have two rational expressions and I want to add them together, would you know how to do that? If I have two rational expressions and I want to multiply them together, would you know how to do that? And if I have two rational expressions and I want to divide one by the other, would you know how to do that? So what is the first one? Give me a general strategy.
Find the least common denominator between the two fractions.
Yeah, that's a little bit more specific. Just give me like a general idea, like something that's always going to work, like a formula for these. Do you remember the formulas?
A times D plus B times C all over B times D.
Right. Now that is a general formula. That sort of strategy is literally always going to work. The difference is it just might be overkill. It might be too big. Finding the LCD is a way to get to a reduced answer in one shot. So the LCD, which is, yes, you should know how to do that, is really a way to actually get to the same answer, but simplify a little bit more before you get to there. And this, of course, applies there, here, right? So working with LCDs can reduce this answer in many cases. Right. So while this would still work, so let's create some space here. So for example, if I had, say, 1 over x plus 1 over x squared, I could actually just apply this formula. Take the x1 times the x squared plus the 1 times the x over the x squared times the x. You notice that you would get x squared plus x over x cubed. Now this is the correct answer. However, it can be reduced, right? So you could factor out an x and you can just cancel these guys, right? So so this is the formula gives this answer. Formula gives this answer. It can be reduced, right? So it's not like it's going to give you the wrong answer. It'll give you the right answer. But if I ask you for a simplified version of the answer, the formula is overkill. Like it'll give you the answer, but you can potentially reduce it further afterwards. Versus, if I did that versus something like 1 over x plus 1 over x squared, and instead I went through creating the LCD. So I would multiply the first fraction by x over x, and then add these two. Notice that I get the reduced answer right away. So LCD gives reduced answer right away. So I don't want you to come away with the impression that somehow the LCD method is like the way to go, or it's the only way to go, or it's a superior method. In terms of simplifying, it's nicer, right? So once you just do things in terms of LCDs, it's like the answer that you get for the most part is going to be simplified already. Whereas if you just mindlessly apply this formula, which works for fractions in general, you'll get the answer, but you might have to reduce it further, which, I mean, if you want to go, you need to know how to simplify rational expressions anyway. So if you get an answer that's not fully reduced, you should know how to reduce it. But that's just something that you should be aware of. When it comes to multiplication, yes, you just multiply straight across. And again, you can reduce this before multiplying, right? Reducing before multiplying is allowed. And it'll make your life a little bit easier. So, so for like an example here, let's say I have 2 over 5 times 15 over 8. Yeah, I could just go and multiply these across 30 and 40. But then, of course, you notice that I would have to reduce this. Versus if I had the 2 over 5 times the 15 over 8, and then I first went, well, you know, I can take the 2 into the 8, goes 4 times, and I can take the 5 into the 15, goes 3 times. And then I would just get the answer 3/4 right away, right? So the general formulas that I gave you guys before with fractions, they still work, they still apply. It's just that now we are learning techniques for how to simplify while we're doing these computations, just to get them in nicer forms, work with smaller numbers. Of course, when you're dividing fractions, it's just keep, change, flip. And then it's AD over BC. And again, you may simplify before doing this. Which brings us to the next section, simplifying rational expressions. When I say simplify, what does that mean? What is the main technique we saw? So I give you a random rational expression and I ask you to simplify it. What should you be thinking?
Factoring.
Factor, right? Factor the top, factor the bottom, cancel common terms, right? So a lot of times students have rational expressions and they kind of want to get somewhere to do something, and I'll see them do things like they'll expand and they'll do all these maneuvers, and I'm like, no, you should be thinking factoring, right? Expanding is the opposite of what you should be doing, and you shouldn't really want to be doing anything else. There are a few cases where you might have to expand in the numerator. You almost never expand the denominator, but there might be cases where in the numerator you expand stuff. But the point is always to expand group-like terms and then refactor, right? So factoring is always what you should be thinking of, right? So you factor numerator and denominator. Cancel common terms. Right? So factor, which was covered on the last quiz. So you know all the variations on factoring at this point. So you should just know if you're asked to simplify a rational expression, or if you're doing some combination and you want to simplify the final answer, you should be thinking factor and cancel, factor and cancel. That is the strategy, right? So it doesn't matter how complicated it looks or whatever it looks like, factor and cancel, factor and cancel. That's what those are. That's the main idea. Okay, that's where you want to be. Domain, we also covered this. We also covered this, so I won't say too much about it. So like A over B, want to find the domain. This is just an intersection of two things, intersection of the set of stuff that makes each component of A and B work with the set of values. So B is not equal to 0. So you never want to divide by 0, but you do have to be aware that everything else needs to work anyway. So without talking too much about that, maybe I'll just give an example. Like if I have the square root of x over x plus 1, there are two things you need. There are a couple things you need. One, numerator needs to work. And two, denominator needs to work. So the components must work individually. And then 3, you just make sure that the denominator is not 0. So in the first situation, for the numerator to work, you need that x must be greater than or equal to 0. So on your number line, you need things that are 0 and bigger. Whereas in the denominator, for x plus 1, anything goes. So yeah, that's fine. And then in the denominator, you need x plus 1 not equal to 0. So this means you cannot be minus 1, right? And then put them together. And you find the intersection. So this is like the overlap. So you have that situation where I had to be 0 or bigger. You also have that situation where I can't be minus 1. Then you had another situation where anything goes. And then you kind of say, oh, well, where does everything work all at once, right? And so the domain of this is going to be everything that's larger than 0, or all x in, right? So for rational expressions, you need to make sure the denominator is not 0, but you also need to make sure that all the individual components work otherwise. So if I only worried about where this was not 0, I should just say, oh, x cannot be -1. But it turns out there are more things that x cannot be. So you just make sure that you're considering that. But domains was something that we've discussed a couple times now, so I won't go more into that at this point. 4, rationalizing expressions with radicals in them. And so the main idea here, it's kind of difficult to explain, but is to use laws of exponents and what is special, I don't remember what I call them, but maybe special factoring formulas, like difference of squares, difference of cubes, sum of cubes. I'm talking about those kinds of things. Factoring formulas to get rid of radical powers. And remember, radicals, how you can think of them is non-whole number powers. Or let's be more specific, fractional powers. Right, so there could be a bunch of situations that you can find yourself in there. So for example, I can ask you to rationalize the denominator. I think and I could say something like, okay, I have x plus 1 over x to the 2/3, right? And the idea is to multiply and divide by something that I can take advantage of laws of exponents and things of that sort. So what would I multiply and divide by here?
I have a question.
Yes.
When it's set equal to each other, are you allowed to cross multiply?
No.
No.
Because I'm being a little bit sloppy here. This equation wasn't given. I'm just saying this is equal to that. So you can kind of put this in another step, right? So I'm starting with, so this was what's given, right? So the question is, rationalize the denominator of this thing, right? And so you are going to say, well, that's equal to this times something else, right? So it's not, the equation wasn't given. So no, cross multiplication is not allowed. Cross multiplication is allowed if you're given an equation. You can manipulate it like that. But here I'm just given an expression and I want to rationalize it. How can I get rid of the fractional power in the denominator is what you should be thinking. What is the nicest, smallest thing that I can multiply and divide by that's going to get rid of that fractional power? Well, what's the closest whole number power to 2/3? The closest whole number to 2/3 is what?
1.
It's 1. What would I need to multiply by if I want the power of x to become 1?
1/3.
Well, not 1/3, x to the 1/3, right? So you can multiply by x to the 1/3 over x to the 1/3. Why? Laws of exponents. If I add the powers, that's going to give me the new power. So that is going to become, in the denominator, x to the 1. And then in the numerator, I would have x to the 1/3 times x plus 1, right? So that now is rationalized. At least the denominator is rationalized. What if I had x plus 1 over the square root of x minus 2? And I ask you again, rationalize the denominator. What do we do here? What do you multiply and divide by?
Square root of x.
Just the square root of x?
Plus 2.
Right, because the square root of x wouldn't completely fix things, because what you would have is, if I multiply the square root of x times the square root of x, it's going to give me x, which is good, but then multiply the square root of x by the minus 2, I get the minus square root of x. So I still have a radical in the denominator. It's not going to fix things completely. So yes, you multiply by what's called x plus 2, x plus 2, and that's called what? What is this thing called?
It's not the reciprocal, right?
No.
The conjugate?
It's called the conjugate. And this is something that's misunderstood. So I want you to realize what conjugate actually means. A lot of people think that conjugate just means change the middle sign, which is not what it means. But if you want to get rid of a square root and there are two terms, that's what it means. And the reason that works is because the denominator here looks like a minus b. If I set my a equals square root of x and my b equals 2, the denominator here would look like a plus b. So by changing the middle sign, it allows me to take advantage of the difference of squares formula. Right, so changing the middle sign works because I'm literally thinking of a special formula in my head, difference of squares. By doing that, what the denominator now becomes is a squared minus b squared, which is going to be x minus 4, right? And this is pretty much a squared minus b squared, right? So now there are no fractional powers in the denominator because I multiply by something to get the powers to be whole. And this is a combination of knowing how the laws of exponents work, as well as special factoring formulas. So here, this is x plus 1 times radical x plus 2. And that is rationalized. Here's another example. What if I were to ask you to rationalize that? So technically here you do multiply by the conjugate as well. But what is the conjugate of this guy? That's the cube root of x minus 1. I don't know if that's visible. What is the best thing to multiply by now? First of all, I want you to appreciate that if I were to do this, would not work. And you're like, well, it worked last time. But understand what that would actually give you, because this would actually be you squaring the first term and then subtracting the square of the second term, which is going to give you x to the 2/3 minus 1. You didn't actually get rid of a radical, right? So just changing the middle sign and multiplying and dividing doesn't work. What would I multiply by?
You do like x to the 2/3 or something involving that. Wouldn't that cancel out the, like, if you change the radical to x to the 1/3?
Yeah. So I think of this as x to the 1/3, and now what do you want to do? You want to find a way to cube both terms, right? So before we wanted to find a way to square both terms because I had a square root. Now if I have a cube root, I want to find a way to cube both terms. How can I get both terms cubed? What would that look like? Well, that would look like the difference of cubes formula, right? Like if I start out with a minus b, and my goal is to get to something like a cubed minus b cubed, that can be done, right? What would I have to multiply by to make that happen? This times what would give me something that looks like that?
Isn't it a squared plus 2ab? No, ab.
No, it's ab. It's b
Yeah,
squared.
b squared.
Right? So it turns out that that is what the conjugate looks like. It's not just a change in a middle sign, right? So it turns out that if I took this and I multiplied by x to the 2/3 plus x to the 1/3 plus 1, that is actually going to give me a nice value. The denominator is just going to be the cube of the first guy minus the cube of the second guy, right? That's now like my a cubed minus b cubed. And the numerator is going to be your x plus 1, x 2/3 plus x 1/3 plus 1. And now that is rationalized. Okay, so you're just taking advantage of the formulas that we learned about. So if you want to get rid of a cube root, you need to cube things. How do you do that? Difference of cubes formula, or sum of cubes formula, or something else. And it works on the flip side. So if I gave you another example, something like x plus 1 over x to the 2/3 plus x to the 1/3. Let's do minus just to be something different. Plus 1, and I actually rationalize the denominator. You should recognize that that denominator is like the quadratic part of the sum of cubes formula, right? So you'd be able to say, well, if I think of this as the square of something, and that's as the product of the two things, and this as a square of something, then multiplying by a plus b is actually going to allow me to cube both terms and end up with something like that. And so what I can do is multiply this by x to the 1/3 plus 1, and multiply and divide by that. What's going to happen to the denominator? Well, it all becomes x plus 1, rationalized. The numerator would now be x plus 1 times x to the 1/3 plus 1. This, in fact, can simplify a little bit. So this whole thing that I mentioned here was just a fancy way of writing x to the 1/3 plus 1. Right? And it's just because I know in theory, I know this should be sum of cubes. I know the sum of cubes formula very well. So I know, okay, if I have something that looks like this, if I multiply it with something like this is what would result, right? And if my goal is to cube the powers, because they're all 1/3 powers, that actually puts me into a nice position. So if I know I want to get rid of a square root, I would tend to think difference of squares formula. If I want to get rid of a cube root, I would tend to think difference of cubes formula or sum of cubes formula. And of course, there are formulas that go higher than this. You have difference of fourths, difference of fifths, difference of sixths, etc., going all the way up. You can use those formulas as well, but I'm not going to test you beyond cubes, right? If you can show the idea with squares and cubes, in principle, at least in theory, you'd be able to show it for anything higher. So that's just something I want you to be aware of. So when it comes to rationalizing, a common misunderstanding is that, oh, I can always just multiply and divide by just changing the middle sign. Doesn't always work. Depends on what the goal is. If you want to get something squared, then yeah. If you have something that looks like a plus b, then you just change the middle sign, a minus b, and multiply and divide by it. Or if you have something like a minus b, then yeah, change the middle sign, multiply and divide by a plus b. But if you have something else, like an a to the 1/3 minus a b to the 1/3, then multiplying by something where you just change the middle sign is not going to work. It'll actually square the terms instead of cube the terms, right? Yeah. Let's see, where else? 5 is equations, just the general idea. We spoke about that already. So maybe the next thing I'd want to talk about is like, let's move into like 6, linear versus nonlinear. And at this point, I mean, we'll cover other kinds of functions later on, but so far I think the focus was on polynomial equations. So the first category was 6.1, was the linear case. And this was an equation that looked like ax plus b equals c, right? And we kind of understood what to do with that. You basically want to isolate the x. You want to have x by itself equals to something that has no x's in it. And you could accomplish that by just performing opposite operations of things that are not x's to move them to the other side. So if I realize that I'm adding a b, so what I'd want to do is just subtract a b from both sides. Opposite operation to remove the b, the inverse operation. The inverse of addition is subtraction. And then I have my x being multiplied by an a. So this means I'd actually want to divide by an a. And of course, here we're assuming that a is not equal to 0, because otherwise you wouldn't even have the variable x to solve for in the first place. So your a would have to not be 0. And of course, that doesn't make that would make sense, that this is what the answer would have to be like. So all linear equations are pretty nice. The thing is, when you have a nonlinear equation, it gets a little bit sketchier. The ideal goal would be to reduce a nonlinear equation to a bunch of linear equations. So 6.2, let's look at the nonlinear case. And so what was like the main strategy? If you were to just describe to someone very concisely how to actually solve a nonlinear equation, what would you say? Right? Your friend shows up 5 minutes before the test and he's like, man, I didn't get to study last night. What do I need to know to solve nonlinear equations? And you had to like, Jhevon is walking in the classroom and you had to say like one thing to your friend. Like, okay, just get this done and you're good, right? Like, what is that thing that you would say for nonlinear equations?
Factor.
Factor. Almost. Clean that up a little bit. This one actually you can't really describe it as one thing, but about 3 short things maybe. Factoring would be step 2 of the thing that you would tell your friend. So it does involve factoring. Because after you factor, what would you want to do? Whoever said factor.
Oh, before you factor, you want to make sure that it equals 0.
It equals 0 because there's a property you want, there's a specific property that you want to take advantage of called the 0 factor property, which means that you need to have 0 on one side. So the thing before you factoring is to first move everything to one side. Right? So once you move everything to one side, so 0, and specifically the number 0, it does not work with any other number. So it's not like you can leave a constant on the other side. Oh, there's a 5 on the other side, just leave it alone. No, no, no. You need to get rid of the 5. It has to be specifically a 0 on the other side. So 0 is left on one side. You're going to factor this, that side, as in the non-zero side. And then you're going to set each factor equal to 0 and solve. And this is applying the 0 factor property. Right, so if you were to be super succinct and try to tell someone how they would solve a nonlinear polynomial equation, that would be how you would tell them. Get everything to one side, factor, set each factor equal to 0. Okay, quiz starts. Now, hopefully, the person would have already known how to factor, and so they'd be fine. Like, if they paid attention the previous week, they'd be able to pull it off, right? They'd be able to walk into that quiz and get a very good grade just by you telling them these 3 things. And this is a part of the reason why I'm spending such a long time in chapter 1. The topics themselves aren't that complicated, but it's very important that you get a lot of practice with it and that you fully understand them, because later on when I'm explaining more complicated topics and I'm just telling you, oh, you just do this, you do this, you do that, if you don't fully understand the basics, it's just going to be like, it's gibberish. Like, okay, Jhevon, whatever you say, man. Like, you're not going to get it. And then you're going to wonder, you're going to be studying for hours and hours and hours. And you're like, why is this so complicated? It looks so easy when Jhevon was doing it in class. But that's because when I was doing it in class, I'm applying very simple rules at every step. But if you don't fully understand those rules, you're not going to get it. It's not going to sink in, right? But so, I mean, I can explain to you very succinctly how to actually go about solving an equation. But if you don't know what each of these steps are, it's gibberish. Like if I tell you factor that side. If you don't know how to factor, then good luck. You're not going to be able to solve the equation, right? So, but this is the short, this is how you would actually get it done. So let's do just an example. Example, solve, like if I were to ask you to solve something like I don't know. Okay, so that's a nonlinear equation. I know it's nonlinear because there are powers of x other than 0 and 1, right? So linear basically just means the only powers of x present are 0 and 1, right? Nonlinear means anything else, right? So, but for polynomials, the powers are still non-negative whole numbers. So yeah, how would you go about doing that?
Add x to both sides.
Right. Is that it? We're good?
And then subtract or add 2 to both sides.
I didn't mean to square that. Right, so I mean, you would just add the x and the 2 at the same time, right? So in one step, you just bring everything to one side. It could work with the other way, but I was thinking of a specific example. Bring everything to one side so that 0 is on that side. Then you would factor the non-zero side. How do you factor that?
Isolate the 2 parts. So x to the third plus 2x squared is in parentheses, or is its own section. And we're going to take.
Okay. What is that called? What he's referring to?
Factor by grouping.
It's called factor by grouping, right? So this is a situation where you do factor by grouping. And of course, factoring has its own thing. I'm not going to go through all the steps. The first thing is to look for the GCF and then blah, blah, blah. Right, but factor by grouping would be the choice here. So the common term between the first two is x squared. The common term between the last two, well, there's just a 1 common between them. So x plus 2 is the common term. And now you end up with a situation where you just have a product of things equal to 0. The zero factor property says set each thing equal to 0. This is a zero factor property. That basically says if you have a product of things equal to 0, one or several of the factors must be 0. So this would say you would set the x plus 2 equals 0, or your x squared plus 1 must be 0. This one here is going to give you no solution, because that would imply that x squared is equal to -1, which is a complex number, and we're not focusing on that in this class. And this one would tell you that your x is -2, and that would be the answer. That would be the solution to this equation, the real solution to this equation, right? So you're solving nonlinear equations. The important thing that you need to know is bring everything to one side, factor that side, set each factor equal to 0. Once you can pull that off, it turns out that once you can factor it, the individual factors, like these guys, will be simpler than the original equation in the first place. And in the best case scenario, you'll be able to break it down into nothing but linear factors. In this case, we could break it down into a linear factor and a quadratic factor. But best case scenario, everyone breaks down into linear factors and you can solve it pretty easily. If it breaks down to something like a quadratic factor, you can use like a quadratic formula or just factor further. But yeah, that's how you'd go about doing that. I think I do talk about, yeah, quadratic formula was the next thing. So the above applies to quadratic equations.
I have a question. On the quiz, do we need to know the steps of the quadratic formula?
No, like it's just a formula. Okay. In steps, you mean like the derivation?
Like, you know how you wrote down the steps, like divide the b term by 2, like the steps in order, basically.
Right. So those steps that's what we call completing the square. So would you need to know completing the square for the next quiz? No. Do you need to know completing the square in general? Yes.
Okay, thank you.
So we derived the quadratic formula using completing the square. So those were the steps that I was writing out. The steps that I was writing out was literally the steps for completing the square. You don't need to know those, but there's going to come a point where you do, like when we get to equations of circles and things of that sort. Completing the square is something you're going to need to know how to do. So the above applies to quadratic equations when they factor if they don't factor, that leads you into 7, which is the quadratic formula. And at this point, you just need to know the quadratic formula, right? So you don't necessarily need to know how it's derived, although it's derived using completing the square, and you should know completing the square. I'll talk about that at some other point, though. So this says if ax squared plus bx plus c equals 0, and of course your a is not 0 because otherwise it's not a quadratic, then your x is equal to, what's the quadratic formula?
Negative b plus minus square root b squared minus 4ac, all of that over 2a.
Right. So it says if you have a quadratic equation, that's how you can solve for the x's. And by the way, this always works, right? It always works, including in the factoring case. It's just that in the factoring case, it'll be overkill. It's kind of like earlier when I gave you those formulas for adding fractions, a plus b over plus a over b plus c over d. You can think of that as ad plus bc all over bd. That always works. Is it always the best thing? Well, no, because sometimes you end up in a situation where you have to end up pulling it back and simplifying afterward. So in the same way, the quadratic formula is kind of like that. It's always going to work in every situation. But it's like sometimes it's overkill. Sometimes if you could just factor easily, like why would you do that? Like if I have x squared minus 4 equals 0, why would I do the quadratic formula? I can just factor that into x minus 2 times x plus 2, and then I get x equals 2 and x equals minus 2. Like I wouldn't need to have to go through dealing with radicals and pluses and minuses and any of that, right? So it always works, but sometimes it's overkill. I'd really only suggest it if you can't factor. So guess I'll give an example of that. X squared plus 3x minus 1 equals 0. Ask you to solve that. You'll notice that can't factor. Which means the strategy that we learned in the last step for nonlinear equations just won't work, won't get us anywhere. And so we would try something like the quadratic formula, right? Because I can't think of two numbers that when I multiply, I get -1, and when I add them, I get +3. So I would immediately just jump into x equals minus b plus or minus the square root of b squared minus 4 times a times c all over 2a. And then I would get -3 plus or minus the square root of 9 plus 4. So I get x equals that. Which, by the way, you should appreciate what that means is that your x can be -3 plus radical 13 over 2, or it can be -3 minus radical 13 over 2. Okay, so that's the quadratic formula. It's just a formula you can hit a quadratic with if the factoring thing is difficult. Because the factoring method is awesome, but it only works if you can factor, right? So if you can't factor, you'd have to do something else. So in the case of quadratics, you can factor the quadratics. Turns out there is a cubic formula. You don't need to know it. There's actually also a quartic formula. So if you have a 4th degree, you can also do it. It turns out, however, for 5th degrees and higher, no such formula exists. So there is no analogous quadratic formula for a polynomial of 5th degree or higher, which is surprising, but it's not something that you need to actually know. I just thought it was a fun fact. It's a very At this point, I don't even remember how much of the story is romanticized, but there's a very romantic story about the guy who proved that it's a French mathematician, very young at the time, called Galois, and he pretty much wrote down the proof for the fact that there is no general polynomial formula for fifth degree or higher the night before he died in a duel over a girl. And it's a whole thing. I'm not going to get into it, right? But he's writing down all these theories, I have not time, but hey, here's something cool, right? That's how he decided to spend his last night on earth, ladies and gentlemen, writing out math. And it turns out that you won't see the kind of things that he was writing down. He was very young at the time, 20, 21 maybe. You won't see the kinds of things that he was scribbling in his notebook until you go to a very high level math class. So literally for like centuries afterwards, we're still discovering some of the things that he wrote down in his book and how useful they are. And it's very abstract, but yeah, he invented a whole new kind of math to kind of prove that how different polynomials with different powers would work. Anyway, I digress. Equation with radicals. So if you have a quadratic, there is something called the quadratic formula. And you have formulas like these going all the way up to the fourth power, but after the fifth power, you are out of luck. You have to get a little bit more creative. So equations with radicals. The main idea here is just to raise both sides of the equation to a convenient power that will kill all the radicals. You might have to rinse and repeat. So raise both sides of the equation to convenient powers to eliminate all radicals. Repeat as necessary. You might have to regroup and repeat as necessary. Then apply previous techniques. So say, for example, if you have like the nth root of some function of x equals some constant, then what you're going to do is you're going to raise both sides to the nth power. Why the nth power? It allows you to cancel the nth root, right? So you're going to do this thing where you're raising both sides to a power. It's very important. You must check your answer afterwards. Because sometimes the act of actually raising things to powers actually can create some false solutions, right? Let's give you a very silly example. We do some more complicated examples, but right now, today's class is just about me trying to get you the essential ideas. So I'm not going to make things too complicated. So example, I have, say, the square root of x plus 1 equals 3, and I want to solve that. Well, my first step is just going to be, well, it's a square root, so squaring both sides is going to make a lot of sense. That's going to help me cancel this radical. So this brings me to x plus 1 equals 9. I can say x equals 8 after that, and then I would check. So I look at the left-hand side, which is the radical of x plus 1, and then I look at the right-hand side, which is just 3, and I need to make sure that these are the same. So this would be equal to 8 plus 1, radical 9 equals 3, and this is equal to 3. So left-hand side equals the right-hand side, and that's good. It means that the value that I chose is a good one. And so I would say x equals 8 is the solution. Right? So that's, let's make it So everything can fit here. So that's how you would go about solving an equation with a radical, right? And if it were a cube root, I would cube both sides, etc. Right? There are times when I need to actually do this process repeatedly. So for example, if there was like another radical on the other side, then I might have to do something else, right? However, you can end up in again, not a complicated example, but just to see how something could go wrong. If I had the same thing, but a -3 on the other side, then if I were to like square both sides, then I would get x plus 1 equals 9. This would mean that my x equals 8. And you might be starting to say, oh, well, that's the answer. Well, you have to be careful, because if you check, what does the left-hand side do? What does the right-hand side do? You'd realize that the left-hand side is the radical of x plus 1. If I plug in 8, that's just radical of 9, which is 3. Whereas the right-hand side is -3, and not the same. So it turns out that this does not work. So the only possible solution is not a solution. So you'd say no solution. So the x equals 8 does not check. Or you can say the x equals 8 was an extraneous solution or something like that is the technical term, but whatever. Just like it doesn't check. Like you have to be aware that sometimes when you're raising things to powers, this goes particularly for if you're raising things to even powers, but I'd just rather you just always check. If you're raising anything to powers to solve an equation, you need to check because you can introduce erroneous solutions. What was the next one? I think it was this 8. 9 was equations with absolute values. So if you have something like the absolute value of some expression A equals B, the idea is you break up into all scenarios, break up into different scenarios, which depending on the context can be 2 or 3 for the absolute value. So it's possible that the absolute value is going to return the original expression, or it might return the negative of the original expression, depending on whether the inside is positive or negative. Then you solve each individually. Previous techniques. And so can I give an example here? Something like if I have the absolute value of x plus 1 equals 4, right? I would say this breaks down into 2 situations. So this means x plus 1 equals 4. And that's in the case when your x is larger than -1. Or I can have minus x plus 1 equals 4. And in the first scenario, I can have my x equals 3. Or in the second scenario, I'd have minus x minus 1 equals 4. And so I would get x equals -5. And so I have these 2 possible answers. And they actually check, right? So I can check 3 plus 1 in absolute value. Well, that's just absolute value of 4. And yeah, that's 4. Great. In absolute value, if I take -5 plus 1, I would get -4, but that's in absolute values. It's going to return 4. Awesome. So those are the solutions, right? So for absolute values, just make the insides negative and positive and break it down into situations. If there are several absolute values, you have to do negative and positive all possible combinations, right? So if there were 2 sets of absolute values, there are 4 possible combinations, right? So the first one positive, the second one positive, the first one positive, the second one negative, the first one negative, the second one positive, the first one negative, the second one negative, right? So you'd have to go through all the scenarios, right? But the idea is you make the inside positive or negative to decide whether or not the absolute values on either side, whether or not the inside is greater than 0, less than 0. But then once you break it down to each individual cases, you're now into one of the previous cases that were dealt with. So you'd be able to deal with that. So that's the thing about equations with absolute values. Absolute values get a little bit more technical when you start talking about inequalities, but that's material for after the quiz. Last thing. So this was the thing that was introduced, equations with rational expressions, which I go into more examples in lecture 12, I think. And the main idea here, is to multiply both sides by the LCD. This removes all denominators. Then apply previous methods. It's also important in this scenario to check your answers when done. Check answers. Got cloudy for a second. Check answers when done. Right, so when you're dealing with radicals and rational expressions, you have to check your answers. There are situations where you can get an answer that makes the denominator of the original expression 0, so you have to kind of worry about things like that. Example. I have x over x squared minus 1 plus 3 over x minus 1 equals 2 over x plus 1. Of course, to find the LCD, you need to factor. We've discussed that in a previous section. How do you go about finding LCD? You factor everybody, take all the common factors, raise to the lowest powers, the highest powers to which they appear. Okay, so here you have like x minus 1 times x plus 1. Which means at this point, you can tell what the LCD is. And then what you do is you multiply both sides by the LCD. So show you what that would look like. So you're literally going to take the entire equation and you're going to multiply by, let's put a middle dot here, x minus 1 times x plus 1. And so you're going to take this entire expression here and you're going to multiply that, you're going to multiply that, and you're going to multiply that. You're going to multiply each term. Notice that in the first term, the entire denominator is going to cancel and I would just be left with x. In the second term, the x plus 1s, the x minus 1s cancel, and I'll be just left with x plus 1. In the last term, the x plus 1s cancel, and I'm left with x minus 1. Now you'll notice it's another equation, and now there are no rational expressions present. So I can use previous techniques. Notice that the only powers of x are 0 and 1, so I realize that this is just a linear equation in disguise. So my idea now, because I know how to deal with linear equations, is to isolate the x. So to do that, let's first break this x out of prison, and let's break that one out of prison. Isolate the x's by moving all the x's to one side, and then moving the other guys to the other side. So this gives me that there are 2 x's on this side, And then I can isolate the x by dividing by 2. And then, of course, you want to check this to make sure, right? But that one seems like it would work. That minus 5 over 2 is not going to make any of those denominators 0. So pretty sure we're okay, but you do want to check to make sure for any other possible issues, especially if it's possible that your rational expressions had radicals in them as well. So you'd end up multiplying by radicals, and then you'd have to raise the powers, and then you have to worry about all that. But yeah, essentially the main idea is multiply both sides by the LCD. It puts you in a previous case, right? And so we learned how this very basic case, how do you deal with a linear equation? How do you deal with a quadratic? Okay, now let's start mixing stuff up. Throw in absolute values, throw in radicals, throw in fractions. Doesn't matter. We know how to actually deal with them. We can take any of these situations and reduce them to a previous case that we've already solved, right? And with rational expressions, the main idea, how you reduce it to one of the cases that I've already spoken about, is to multiply both sides by the LCD. Yeah. Yeah, so just about 2 minutes to go. But that's basically it. Those are, if you're good with all these techniques that I've spoken about so far today, you should be good with the quiz next week. So we kind of did a mini crash course in all of them. But yeah, in class we go into a lot more detail, a lot more examples, and I write everything out. I just wanted to make sure that we had the essential ideas down, and those are them. So any final questions before we wrap up? Okay, we're gonna stop there. So try to get through lecture 11 by today. Good idea to watch at least the first half of lecture 12 as well. Get homework for 1.5 up to 1.5 done at least. That'll put you in good standing for the quiz. If you wanna go further, you can look into inequalities, equations of lines, equations of circles, midpoints, and distance. And yeah, have a good weekend, have fun studying. Good luck on the quiz next week. No class on Monday, no anything on Monday because it's a holiday. Our next class, the quiz, is on Wednesday, which follows a Monday schedule. Okay, so without any further ado, I guess that's it.
Thank you.
Okay. Awesome. Okay, we're gonna wrap up there. Everyone take care, have a good weekend, and I'll see you in the next one. Ciao.